All right, it's your favorite time of week. It's time for the homework review. The homework review will start this week with a magnetic moment calculation. So we're going to have a current, in this case 20 amps. Need to stabilize that a little bit. Going around this cylinder along the edges, and that's going to have a radius here of 5 centimeters and a height of 10 centimeters. So this is actually a square in cross section. If you were to cut it in half, cut it along along a diameter. And what we'll do is we'll find the magnetic moment of the loop, and then we'll do two things with it. One, we'll model it as a dipole so we can get some charges, and we'll see what those charges are. And then we'll figure out what the force, or the torque, excuse me, on it if we put it in a 2 Tesla field at this angle, which is 30 degrees. So the magnetic moment, that's pretty straightforward. That's M equals IA. The area in this case is the area. So if the current's going around the loop, then the area is the area of the cap. It's a cross-sectional area. It's not the area around the cylinder. It's the area that the current goes around. And so that area is pi r squared, which is pi times 0.05 meters squared, which is 25 times 10 to the minus 4 times pi square meters. All right, so that means I, which is 20 amps, times A, which is 25 meters squared, times pi times 10 to the minus 4 meters squared, is then equal to 20 times 25 is what is it, 500? 2 is 50, yeah, 500. So we have 500 pi times 10 to the minus 4, which means we have 0.5 pi times, that's amps meters squared, times 10 to the minus 1 amp meters squared. So that's 1/2 pi divided by 10, which is 0.157 amp meters squared. So that's the magnetic moment. Found the magnetic moment. Let's do a couple of things with it. So first we're going to pretend that this is a dipole. So remember the dipole approximation pretends that, you know, the force on one of these poles, the top or the bottom here, is going to be Qm times the field, B, and in the direction of the field. So by making the charge approximation, we're going to assume you have the same force law for these fake charges as you have for an electric charge. And when we take something like this, what we do is we say, okay, well, we know the distance, we know the length of this thing, and so we have a dipole strength that's equivalent to that charges that you'd have to get the same moment, right? So we found the moment from the current loop. Now we want to find the moment from the charge, which is the same again as in the electric dipole moment, which is P equals QD. Now we have M equals QMD, or I guess I should say H, the height. So QM, that magnetic charge, is equal to the magnetic moment over that height, which is the 0.157 amp meters squared over 10 centimeters, which is 0.1 meters, which is 1.57 amp meters there. Okay, so remember, amp times meter, an amp meter, is the magnetic charge's units. So the magnetic charge has units of amp times meter, and the electric charge It's still ugly, but it's a lot better than it was when I started this. Is 1 coulomb, or an amp times a second. So you can see how these are related, and probably they're actually related by the speed of light, so that something like this is actually really, really small. So you probably want to divide this by the speed of light to compare it to the strength of a similar electric charge. So that magnetism is quite weak comparatively. And one other thing we can do is find the torque on this. And the torque, we said, was partially the strength of the moment. Oh, wait, this is the field, and the moment is this way. Partially the strength of the field, so the greater the moment, the greater your torque. So something that has a stronger magnetism feels more torque from the same field. And the stronger the field, the greater the torque. So this is something that is, when you put something in a larger field, then it gets a stronger torque. And then we get a sine theta. So we get this sine theta here, which is 30 degrees, remember. Because there's no torque if they're aligned, right? So if they're aligned, since basically the torque is trying to pull B to M, right? If they're aligned, there's no torque. So that's where the sine theta comes from. All right, so that M we calculated was 0.157 amp meters squared. B is 2 Tesla. And sine of 30 degrees is 1/2. So we can get rid of the 2's right away, and we just have 0.157. That's going to be Newton meters. Okay. So there we did it. We found the magnetic moment, and we did 2 things with it. One, we found the magnetic charge in the dipole approximation. Now that's not completely, well, yeah, it's not completely academic, because it's something that you'll do if you're a magnetic modeler. So for example, if you were a magnetic modeler in the hard drive industry, you'd be doing something like that. And they do the modeling with these fake magnetic charges that don't really exist. It's more complicated, but this is sort of how it begins. And then we also used it to find the torque on the actually the magnetic moment wants to come down to here. So that's part A. Part B, or number 2, to be honest, is the long one. This is something I used to do a lot, right? Designing magnetic coils. So in this case, we've got a system here where we want to figure out how many turns we have to put through here. And then we want to figure out what the maximum field is at the midpoint. So these are called Helmholtz coils, which means they have a very uniform field in the middle. It's not perfectly uniform, but it's quite uniform, and that's good if you're trying to do measurements, as you want to have these Helmholtz coils be Helmholtz coils, so you can have a nice magnetic field in there that's uniform, so you don't add any issues due to inhomogeneity in the field if you're doing a measurement. So I'm going to start with having you look up the resistance for the American wire gauge. So the American wire gauge is going to give you a resistance for the 22 gauge copper wire of 50 microohms per meter. Okay. So if you look that up on Wikipedia, or probably anywhere else, they better be the same. You're going to get this number. So the resistance, this is in microohms per meter, and this is going to be in ohms, is R times L, right? So that means that if we're trying to match to 50 ohms, then we have to divide by this 50 milliohm meters. So you divide by the 50 milliohm meters and you get 1 times 10 to the 3 meters, which is 1 kilometer. So you need a lot of wire to do that. And so now when you do these things, you generally, actually they have machines, but I've always had to spool them by hand. So if you're spooling these by hand, then you have to figure out how many times you have to turn the thing, right? In the best case scenario, you've got a lathe, and you just count, right? And the lathe actually has a counter, so it makes it fairly easy. But you just have to sit there and make sure that all of the, just mount that on a lathe. The lathe has a counter on it. You just have to make sure all of the wires go in there well. So we want to figure out how many of these go on there. Well, the number that does that is going to be like the length of wire, that 1,000 meters, over the circumference of your spool. So your circumference of the spool is 2 pi r, or I'm out of r's. So that's 2 pi times 0.05 meters, which is 0.314 meters, I believe. Right? 5 times 2 is 10, so 0.1, yeah. So 0.314 meters. So that means we have 1,000 meters, 1 kilometer, over 0.314 meters, which is 3,183 turns. So that's how many turns we have to do there to get that resistance. Now we want to figure out how much current we get from, we need to figure out how much current we get from the maximum output of 20 volts. So the reason why we did this impedance matching to get this to 50 ohms is so it'll match our power supply so we can get the full 20 volts out without losing any current. So we'll use Ohm's law for this. E equals IR. E is 20 volts. I is what we want. R is 50 ohms. So we divide both sides by 50 ohms, right? Equals 20 volts over 50 ohms equals 0.4 ohms. No, amperes. Oops. So that's good. Now the reason why we did these last two things is we want to find that magnetic moment. So that magnetic moment is the number of times you go around this thing. So each time you do this, you get one factor of the magnetic moment of IA. So the current keeps on going around here n times, so each time it goes around, it adds to that magnetic moment because it's in a steady state. So, you know, an electron's going around here through one part of the loop, but through the next part there's another electron going at the same speed, basically, is what's going on. So if you have multiple loops, you have 3 loops, you'll have the same current going through each one of those 3 loops, which each one will give you a magnetic moment, so you'll get 3 times the moment. Of course, we didn't get 3 times the moment, we got 3,183 times the moment. The current was 0.4 amperes, not ohms, amperes. What do we need? The area. Oh, I didn't calculate the area. Okay, the area is pi r squared, right, which is 3.14 times 0.05 meters squared, which is 3.14 times 25 times 10 to the minus 4 meters squared, which is 78.5 times 10 to the minus 4, excuse me, meters squared. So that's 78.5 times 10 to the minus 4 meters squared. I didn't do anything to change the number. And that gives us a number, and that number is 9.99 amps. So I may change my mind and go to amperes. I may change my mind and pretend like it's 10, depending on what everything looks like. Probably not, but I may. So now we want to find the field here. Now remember, we have a magnetic moment from this, and we have a magnetic moment from this, which means the field here will be the field, right? Magnetic moment is going to be the field from 1 plus the field from 2, and they're actually both going to be the same number, right? Because this is half a radius back and this is half a radius forward. So that's basically 2 times one of them. So we have 2 times mu naught m over 2 pi times r squared plus r squared, right? Little r squared is just little r is 1/2, right? Little r is this thing. It's half a big R. So if little r is half a big R, then we have 2 times mu naught m over 2 pi over, oh, this is 3/2. Too much of that. We have a big R here to the 3/2 that we've pulled out times 1/4 plus 1, which is 5/4, just a pure number, 5/4 to the 3/2. And we can get rid of that 2. So we have B equals mu naught is 4 pi times 10 to the minus 7 Tesla per amps per meter over pi times r to the 3/2. That's 0.05 meters to the 3/2, and 5/4 to the 3/2 is clickety click click click. According to my calculator, it's 1.95, and I forgot the basically 10 amp meters squared. It comes here. So let's see, what does it do? Well, that gets rid of a pi, and let's see, we have 10 to the minus 7, 0.05, that's 10 to the 6th, divided by 3, blah, blah, blah. So that's 0.0229 Tesla, or 22.9 millitesla. And that is about it. That's basically designing this. This gives you about 22.9 Tesla, 229 Oersteds, which means that it's a little bit stronger than normally how I'd get. You usually get about 50 to 100 with one of these things. So probably you don't want to send the 0.4 amps through this. I'm going to pause because the garbage people are going to be coming by for a little while. Okay, hopefully that's recording. Is that recording? I see the number changing, so it is recording. Okay, so I know what I'm going to do. I'm watching to see if any of you come into office hours right now, but I need to make sure all my windows are arranged so that I can see you. I should have thought of that before I did this. So I need to make sure that I can see when somebody shows up. All right, so next, what is the field coming off the wire? All right, so I've got these two wires basically, and so yeah, I've got these two wires, and what's happening here? We've got one wire that we know what its current is, another wire that we don't know what the current is, but we know how far it's been pushed up. So it's connected here by springs. So there's a spring here and there's a spring here. I just didn't feel like trying to figure out how to draw those because it's a lot of extra time. So we want to find this current here. So what we need to do is we need to figure out basically what the force is. Find the force basically because we know how much it's compressed, and that you're going to have to balance forces for that. Probably should have drawn a free body diagram. I forgot to draw a free body diagram. I'll do that in just a second. Right, so we've got the force from the magnetic field with the force from the spring balancing out, so that if we find the force from the spring, we find the magnetic force, and we can use that to find how much current is going through here, because the force is going to be equal to the current going through here times V times L. We know what L is. It's 50 centimeters. And we'll find what B is here, right? So then we should be perfectly fine. So the field from a wire is mu naught I over 2 pi d. And let's see what else. Next we can just substitute things in here for this one. So mu naught is 4 pi times 10 to the minus 7 Tesla per amp per meter. This guy has 1 amp, so we're finding this field that goes through at the point where the wire is parallel to this other wire. I is 1 ampere, that's what's causing it, right? Over another 2 pi, so we can get rid of that, times d, which is 2 millimeters, 2 times 10 to the minus 3 meters. So we can get rid of that other 2. So that B is going to be 10 to the minus 4 Tesla amp per meters. Amps cancel, meters cancel. So we have 10 to the minus 4 Tesla, or 100 microtesla. All right, I think that's the last of the dump trucks. Do not know. All right, so we wanted to, like I said, we want to find the force here from this guy, which is the same as the force on that guy, which is the same as the spring force coming up this way. Since we know what the spring force is, which is K times X, we just need to do 1 kilogram per second squared times X, which is the distance, which is 2 millimeters. So that's 2 millinewtons, right? So 2 kilogram millimeter per second squared is equal to 2 milli, so 10 to the minus 3 kilogram meters per second squared, which is equal to 2 millinewtons. All right, so that's not much of a hassle. let's see, what's the last bit? The last bit is the current going through the short wire. That was where we take the force, which we know is IVL, to find the current. So that's I is equal to the force over B times L. Found B, we know L, we found F. So that is 2 times 10 to the minus 3 newtons over 10 to the minus 4 Tesla times 2 times 10 to the minus 3. Is that right? Oh no, this is L, it's 0.5 meters. 0.5 meters, all right. So it's this distance, 50 centimeters, not this distance, 2 millimeters. So that's 0.5 is actually 1/2. So that's actually 4 times 10 amperes, which is 40 amperes. All right, so basically that's how to get the force out of this. So this is a little bit tricky. Well, this isn't very tricky, but I mean, like most of these, you have to do a bunch of things. But the only tricky part is you have to recall that Newton's first law, that's not supposed to be a trick actually, that's supposed to be the main point of all of the sequence, is that, you know, if you use Newton's first law, you know, Newton's laws are the big things, you can balance out the spring force and the magnetic force, right? They're the same number in opposite directions. Okay, so the last part is going to be protons moving in a field. This is a little bit different from the other one that I did. So this one, he's actually moving around in a helix like that. And so there might be a little bit too much in this, but basically what we're going to do is, in the first part, we're going to figure out what the radius of the helix is. So this guy comes in and then these two fields are turned on. So we'll figure out the radius of this circle. Then we'll figure out how high it goes in one turn. So if it goes around the field 360 degrees, how much higher has it moved? And then we do one of these weird things where you say, okay, if you go up a radius distance, which is, oh man. You go up a radius distance, how far is it? So the question is at this point, is that going to be larger or smaller? We'll find out in a second, right? Because we have to find the radius. We have to find how far it goes up in one turn. The first is the radius. We do that like we did in class. EVV is MP V squared over R. And we can get rid of one of those V's. Just want to find R, so R is equal to the mass of the proton times the velocity over the charge of the proton, which is the same as the charge of the electron times the magnetic field, which is 1 Tesla. The mass of the proton is 1.672 times 10 to the minus something big, 27 kilograms. The velocity we said was 100 meters per second here. E is 1.602 times 10 to the minus 19 still. And B is 1 Tesla. So this is the only hard part of the calculation, and it's so hard that you have to use your calculator. Obviously, it's just a little bit over 1. It's 1.04. And then we have to multiply that by 100 for this, times 10 to the minus 27 plus 19. That's kilograms meters per second Coulomb Tesla, whatever that is. And this difference here is 8, plus 2 is 6, so that's 1.04 times 10 to the minus 6 meters, 1.04 microns. Okay, so the radius that this proton makes is really, really small. All right. Now we want to figure out how high it rises in a single turn. Does it do something like this, or does it do something like that? Right. So that's what we'll figure out next. And we'll have to do that with kinematics. You know, the distance if it starts off going in the plane, the distance goes up is 1/2 at squared. So we have to find the acceleration. The acceleration is equal to the force over the mass of the proton. The force is, in this case, the electric field force. So the magnetic field force, this guy right here, is making it spin. The electric field force is pushing it up. So that is E times E over MP. All right, so that's 1.602 times 10 to the minus 19. Again, we have a 1.672 times 10 to the minus 27 here. Right, so that's actually going to give us a very large number. Right? Times a 200, okay, that's coulombs, kilograms. Volt per meter is in newtons per coulomb. So that's 200 over 1.04. Times 10 to the 8. Coulombs cancel, meters per second squared. So that's actually 0.9. How would I want to say this? 1.916 times 10 to the 10th meters per second squared. That's a whole lot of acceleration. Right, so we add in another one for each one of these steps. So that's a lot of acceleration. And we need the time it takes to go around in a circle. That's just going to be 200 meters per second times the time is equal to the circumference, which is 2 pi r. So that is t equals 2 pi times 1.04 micrometers over 200 meters per second. Okay, so let me go to the calculator and cancel out the 2's. So that's times 10 to the minus 8 meters, right? Micro is 10 to the minus 6, and then we divide by 100. So we have 3.14 times 1.04 is 3.26, or not meters, this is meters per second, so this is seconds. So we have 32.6 nanoseconds. So D is equal to 1/2 times the 1.916 times 10 to the 10th meters per second squared times the 32.6 nanoseconds, 10 to the minus 9, squared, which is about what, 10.2 times 10 to the minus 6 meters. So that's about 10 micrometers. Okay, or 10.2 micrometers. Okay, so we see that this number is somewhat larger than this number. About 10 times larger. Every time a little dot shows up, it screws up. So that's a 10.2. That's a 3.26. Strangely, about half of that because I forgot the 2 there. I don't know what that's about. So now we need to find the percentage of a turn. Well, we do the same thing now. We need r equals 1/2 at squared, right? But over here, the distance was equal to 1/2 at squared, right? So the ratio, t over t squared is equal to r over d, which is 1.04 micrometers over 10.2 micrometers. All right, so t over t is equal to the square root of that, which is about 1/10 or something, which is about 0.319, or about 32%. All right, that's changed a little bit because I screwed up here and it propagated. So that's 32%. That's 3.26 times 10 to the minus 8 seconds. That's 10.8 micrometers. All right, so that's how you do the last one, as long as you remember that 200, it doesn't change from being 200 up here to being, no, it's 100. So I was right the first time. I'm sorry, because I got confused about those two numbers. So I was right the first time. Ignore all the stuff where I was thinking too hard. All right, that's about it for today. We will get on with more interesting things for you to do in just a moment. Bye now.